Hey everyone, imagine you're watching an intense cricket match and the score is climbing, but you want to see how your favorite team is performing over time. That's where graphs come in. By plotting the runs scored per over on a graph, we can instantly see if the team's performance is picking up or going down. It's like having a pulse on the match without watching every ball. Today we'll explore how graphs are powerful tools to analyze and visualize all kinds of data, not only in sports but in science too. So let's dive in. But students, before we start, please don't forget to like, share and subscribe to our channel. That really keeps us going. Let's learn together. Hello students, you should be very excited about today's class. Why? Because today's class is about graphs. I think you should remember in the previous classes I was talking about the various possibilities of numericals that we can get, but we were not looking at the numericals including the concepts of graph. In fact, graph is almost included in every numerical related with this chapter motion. So you should be very thorough with the concepts of graph, be very particular about what exactly the graph is representing. You should not only know how to draw a graph, you should also know very clearly how to interpret or extract information from a graph. So I hope you are all excited and very enthusiastic about learning this. So we shall start. So the first thing that I would ask, do you exactly know what does a graph do? So when we say we are drawing a graph of y versus x, then do you exactly know what it means? So it means that x is the independent variable. X is the independent variable. So what are we doing? First of all, we are changing x, and by changing x, we are seeing the corresponding change in y. So can we call y as the dependent variable? We can call y as the dependent variable. So how easily a graph would be able to represent the information? Think about it. You have one option to see the entire data in the form of a table, and the second option to picturize it with the help of a graph. So graph is always going to be very helpful when you have to do any quick interpretations or quick extraction of information. So we shall start now again and talk about what exactly this means. So here we are changing x, and for every value of x, we are seeing the corresponding value of y. Let's say this is a point, this value is, let's say, x1, and the corresponding value is y1. Then if we change it to, let's say, x2, and the corresponding value changes to y2. So this is going to be our first observation point A. This is going to be our second observation point B. So if we join them, then what we get is a graph. How does it help us? It helps us in knowing certain kind of trend. So for example, what you are seeing here right now is on increasing x, y also increased. So we can say that y is proportional to x, or we can say y increases with x. On the contrary, if I would have drawn a graph like this, where A is a point, let's say x1, corresponding value is y1. Now there is another point, let's say x2, and corresponding value is y2. Then what do you feel? On increasing x, the value of y is rather decreasing. So we would say that y is decreasing with x, or y is in inverse proportion with x. So this is just the basics of it. You might already know this because of your math, but you should know the background. How are we going to use this in physics? Because in physics, we many times want to see how one physical quantity affects another physical quantity. All right. So now we start talking about the significance of gradient. So what should we talk about now? The significance of gradient. So what do you mean by significance of gradient? Let's understand what exactly gradient tells us. Okay, so again, let's think about it again. Let's say this is a point A, this is, let's say, x1, and the corresponding value is y1. So I'm doing the same thing again. Then there is another point, let's say B, the value is x2 and the corresponding value is y2. So let's say this is B. So now what do you mean by gradient? So in very simple language, you can say a gradient is just like a slope. So how high you are rising. So in very simple terms, you can define gradient as the ratio of rise over run. So what is gradient? Gradient is basically the ratio of rise over run. In simple terms, it is also called slope. It is also called slope. So what do you mean by that? So let's say you were at A, now you go to a value B. This is how much you have traveled along X. So this is your run, right? And this much you have you have rise from A to B. So this is your rise. Okay. So what is the run basically? So it is x2 minus x1. It might feel like a math class to you, but I will tell you what is its significance in physics again. What is the rise? So it is y2 minus y1. So again, you were at A, you went up to B, this much you have moved along the horizontal, x2 minus x1, and this much you have risen in vertical. So y2 minus y1. So what do you mean by gradient? It is the ratio of rise over run. Listen to me very carefully. So is it equal to y2 minus y1 over x2 minus x1? So it is equal to y2 minus y1 over x2 minus x1. What does this indicate now? So it indicates how much has y changed with changing x. So if the gradient is more, that means the graph should be more steep. Why? Because you are rising more. Okay. On the contrary, if let's say the graph looks like this, then it is lesser gradient or it is less steep, then you are rising less. So what is the difference between this graph and this graph? So you will say that in the first case, y is changing more rapidly with x, while in the second case, y is not changing that rapidly with x. So what does that mean? That means more steep the graph is, more is y depending on x. Think about what if the graph is like completely horizontal? Then you would say y is not changing with x at all. So you can say that y is independent of x. Y is independent of x. Why? Y is not changing at all with changing x. So yeah, so I will come back to that example. What if this data is representing, or this graph is representing you going on a trip, and y is representing your distance and x is representing the time. Okay, so let's imagine that this is a graph for distance versus time. So it is telling you how distance is changing with time. So what should this graph mean then? So it should be the ratio of change in y, that is change in distance, divided by change in time. So it is change in distance over change in time. Can you think what it is? Distance divided by time. Yes, I think you've guessed it right. It should be the speed. It should be the speed. So the gradient is indicating the speed. In fact, you can now remember it forever, that the distance versus time graph, gradient will give you the speed. So more gradient means you are covering more distance in less time, so it is more speed. Less gradient means you are covering lesser distance, so it is less speed. Okay, so I give you 1 minute, you can copy this down, because this basic knowledge of gradient is going to be very important and crucial for us for understanding why we are drawing graphs and how they are going to help us. All right, so I give you 1 minute, you can write it down, then we will move on to the next slide. All right, So next we are going to talk about various cases. So just now we had a discussion that if we are drawing distance on the y-axis and time on the x-axis, obviously we are getting distance for every time, but we are also going to get the speed with the help of gradient. Okay, so the first case that we are going to talk about for distance versus time. So now we are starting with the physics part. So we are drawing the distance versus time graph. So again, distance is on the y-axis and time is on the x-axis. So we are tracking how distance is changing with changing time. So the first case, what is the first case? So the first case is that the object is at rest. So imagine you are on a road journey and you stop somewhere and then you don't move forward for a little bit of time. So what does that mean? In that particular case, you would mean that your distance has become fixed. So it should be a flat line. It should be a horizontal line. So even if time is increasing, the distance is not increasing. What is that indicating? That's indicating that the object is at rest or it has become stationary. Okay. Second case, when the object is moving at a uniform speed. So when this is saying lower speed, we would always mean uniform speed for now. We will always mean uniform speed for now. Okay, so we are talking about object moving at lower speed. So what should the graph be like? Object is moving, so obviously distance is increasing, but it is increasing at a lower rate. So should the graph be like this? I think you should all imagine yes. So it is a constant gradient. The gradient is not changing. The slope is not changing. So it is indicating a constant speed but of some lower value. But now if you choose to draw the graph again, but for an object moving at a greater speed, again assuming a constant speed, then what should the graph look like? Think about it for once. What should be the difference now when you draw the graph? I think you should all imagine it should be a graph again that is going to be a straight line graph with a constant gradient, but with a higher gradient, with a higher value of gradient, with a higher slope. So can you compare these two graphs? The blue graph is showing a constant speed of lower value, while the red graph is showing a constant speed of higher value, right? So this is about the distance time graph. Again reminding, this is our first step towards the graph. Don't hesitate. You should first know that we are taking one step forward. So it is only the case that we are discussing which is uniform speed. So right now we have not included the concept of acceleration, but we'll go there. But one by one, first you should all be able to imagine why these graphs are like what is showing on the screen. All right. I think you should make a note of it. You should make these graphs for the three possible cases and you can easily make the comparison that the speed is more in this case as compared to the first case. All right. I give you 1 minute to copy this down and then we'll talk about the next thing. All right. Next, we should take an example to understand exactly how do we use a distance versus time graph. So we have a train journey here. Graph shows the distance versus time for a train journey. So it is showing the distance versus time for a train journey. Okay. What are you seeing on the x-axis therefore? Time. And what are you seeing on the y-axis? The distance the train has traveled. Be very particular about the units. It is kilometer here and time is obviously showing as 1 p.m. 2 p.m. So every one block is equivalent to 1 hour. Okay. So what is the first question that they are asking? So first question they are asking, how far did the train travel? Oh, so it's a very straightforward question. They are wanting just to know how far has the train traveled. So this is the last point of the journey. Can you all see that? So what is the corresponding distance? So can you all see it is 1000 kilometers. So what is the answer to the first part? The answer to the first part should be 1000 kilometer. How much has the train traveled? 1000 kilometer. What is the train's average speed in kilometers per hour? All right. Again, let's revise the concept of average speed. You all should remember average speed is used to summarize the whole journey with a single value of speed. So, average speed, what is that going to be? Total distance divided by total time. Total distance divided by total time. Okay, so what is the total distance? We have just now known that. So it is 1000 kilometers. Okay, and what is the total time? So what is the last point? What is the corresponding time? So it is 5 p.m. So how many hours is it? 1, 2, 3, 4 and 5. So 12 p.m. you started, 5 p.m. So it is total 5 hours. So we shall divide it by 5 hours. Be very careful. So the answer is going to be 200 kilometer per hour. So it is not meter per second as we normally do, because here the distance is in kilometers and time is in hour. So the speed is in kilometer per hour. Though we can have a small discussion on this. What if we have to convert this into meter per second? So I hope you all know this, that 1 kilometer means 1000 meter. Be very clear about this. And 1 hour is like 60 into 60, that is 3600 seconds. So from here, doing this calculation, you can know that this is going to be 1000 and this 0 will cancel out. So this is going to be 1000 divided by 18, whatever the calculation is going to be, 1000 divided by 18 meter per second. So this is the average speed. So we have summarized the whole journey right from O, A, let's label these points B and C. So right from O to C, the average speed is going to be 200 kilometers per hour, or you can also convert this to meter per second. All right. So now we shall talk about the third part. What is the third part? The third part is maximum speed attained by the train. So this is where our gradient concept is going to be used now, because we are wanting to know the speed. So you would say that let's first understand what are the 3 sections representing. Okay, so one by one, I give you 1 minute. You can pause the video and copy this down. Then I will clear the board and then we talk about the third part. All right. So now let's talk about the third part. So what is the third part? What is the maximum speed attained by the train? So one by one, let's again focus on the 3 parts that we have: O, A, B and C. One by one. O to A, we see a constant gradient. So there is a constant speed, right? Then A to B, can we say that the train is at rest? So something has happened. For exactly 1 hour, from 2 p.m. to 3 p.m. the train is not moving at all. Okay, and then B to C, it is again moving with constant speed. So there are 2 different zones in which the train is moving with constant speed. Let's find that out. So let's talk about O to A first. Okay, let's talk about O to A first. So O to A, we talk about the gradient. So speed is going to be the gradient. Now what is gradient? Change in distance divided by the change in time. We can also call it the ratio of rise over run. So what is the rise? The rise is going to be 400 minus 0. And what is the run? 2 minus 0. We can take 12 p.m. as 0. We can take obviously 12 p.m. as 0. It's going to be how much? 200 kilometers per hour. Okay. Then let's talk about B to C. Okay. Then let's talk about B to C. What is going to be the speed now? again the value of gradient. Everyone please focus. So gradient, now B to C, okay, what is this going to be? So what is the rise and what is the run? Think about it. I give you 1 second, you think about it. So the rise is going to be from 400 to 1000. Okay, so this value is 1000 and this value is 400, and the run is from 3 to 5. This value is 5. Okay, this value is 5. Corresponding C value is 5. So what is the rise? What is the rise here? So it's going to be 1000 minus 400. 1000 minus 400. This is the rise. And what is the run? So 3 p.m. and this value is 5 p.m. So from 3 p.m. to 5 p.m. I can write this as 5 minus 3. Okay, I hope you are able to understand. So this is going to be 600 divided by 2. So that's going to be 300 kilometer per hour. 300 kilometer per hour from B to C. So there are two different zones in which the train is traveling with constant speed, O to A and then B to C. And you can clearly see O to A, the gradient value is coming out to be 200 kilometer per hour, but B to C, gradient value is turning out to be 300 kilometer per hour. So what is the maximum speed attained by the train? Answer is going to be 300 kilometer per hour when you're going from B to C. I hope you're able to understand this and you're able to understand the significance of gradient in context of distance versus time graph. Again reminding you, you are definitely getting the distance on the graph, but you are also getting the speed. It's hidden somewhere here only. If you have to look for it, just it's in the form of gradient. So keep in mind, you have to calculate the gradient whenever they are asking for speed from a distance versus time graph. All right, so you copy this down and then we will move on to the next category of graph, which is the speed versus time graph. You can also say velocity versus time graph. They are not very different from each other. How they differ, we'll talk about that. But right now you can copy this down and then we move on to the next section of graph, which is the speed versus time graph. Okay, so now let's start with the speed versus time graphs. Speed versus time, or we can say velocity versus time. So what is the difference? See, the only difference that graphically there is that velocity can be positive as well as negative depending on the direction, but speed can only be stated as positive. Next, speed and velocity will always have the same value at any given instant. Again, the only difference is that in velocity you try to include the direction also. So sometimes we might refer these graphs as speed versus time graph, and sometimes we also call them velocity versus time graph because there is not much of a difference graphically. All right, so when I say speed versus time graph, I want to have that discussion again. So let's say I am discussing speed, or let's say velocity on the y-axis and time on the x-axis. Okay, velocity on the y-axis and time on the x-axis. Okay, so let's say there is again a graph like this and there is a point, let's say A, having corresponding value of time as t1 and the corresponding value of velocity as v1. Again, we are drawing velocity on the y-axis and time on the x-axis. So the values are t1 and v1. Similarly, there is another point B whose y coordinate, that is the velocity is v2 and the time is t2. So think about it now. What is going to be the gradient of this graph? What is going to be the gradient of the graph? So gradient of this graph is going to be again the ratio of rise over run. So what is the rise? So you would say it is v2 minus v1, and what is the run? It is t2 minus t1. So what is the gradient of this graph? Gradient of this graph is going to be v2 minus v1 over t2 minus t1. So far so good. I don't think anyone should have a problem. Can we rewrite this as delta v over delta t? That is change in velocity divided by the change in time. Is it also the acceleration? How many of you would remember that ratio of change in velocity to the change in time, or we can say change in velocity divided by change in time? It is nothing but the acceleration. So the gradient of velocity versus time or speed versus time is telling you how fast the object is accelerating. Yes. On the contrary, if this graph is a decreasing graph, as we have talked about, then you would say the corresponding value t1 and v1, then the next value is going to be t2 and v2. So on increasing time, velocity is decreasing. Can you all see that? So this is point A and this is point B. So on increasing time, velocity is decreasing. So can we say that the gradient now is going to be negative? The gradient now is going to be negative, or we can say this is the case of negative acceleration or deceleration. This is going to be the case of negative acceleration or deceleration. So just like distance versus time graph, the gradient was giving us the speed. Now velocity versus time or speed versus time graph, the gradient is giving us the acceleration. Positive gradient means acceleration, negative gradient reducing speed means deceleration or negative acceleration. Okay, so make a note of this. Again, distance versus time, gradient gives us speed. Speed versus time or velocity versus time, gradient gives us acceleration. Okay, one more thing I want to talk about. We are getting velocity here on the graph. We are also getting the acceleration with the help of gradient. One more thing I want to talk about, but you make a note of this. You try to note it down in your notebooks. Draw these graphs. I will wait for a minute. All right, now I'm removing this. I wish to draw a graph again for speed versus time or velocity versus time. Okay, again reminding there's not much of a difference, just that velocity we will also include the direction, but magnitude wise speed and velocity are the same at any given instant. So we are drawing the speed versus time graph. I want to take a very simple case where the object is moving at a constant speed. So what are we talking about? We are talking about uniform motion. So what will be the graph like? You would say it will be a horizontal line. Why? Because the speed is constant, so the speed is not changing. Let's say this is a point where the time is t1. This is another point where the time is t2, and the value of speed is, let's say, v, or value of velocity is, let's say, v. Okay, listen to me very carefully. We have just known that velocity or speed is change in distance divided by change in time. Okay, change in distance divided by change in time. That is the velocity. That is the gradient of distance versus time graph. This is the value of velocity. Now look carefully. What is v? Distance or displacement divided by time. Yes, so delta s divided by delta t. So what is delta s then? So it is v times delta t. V times delta t. So this is v, and this whole thing is going to be delta t. So what is v times delta t here? You would say it is the area. This area of this rectangle. Is it a very great finding? That speed versus time graph or velocity versus time graph, this area under the graph, area under the graph is giving us the distance, is giving us the distance. So what do we have to say? A speed versus time graph is capable of giving us everything in that sense. It is obviously giving us the speed, its gradient is giving us the acceleration, and its area is giving us the distance. So again reminding, speed versus time, be very careful about this. Gradient is giving us the acceleration as we have just understood, and area under the graph is giving us the distance also. So you are getting the speed on the graph itself, the gradient is giving you the acceleration, and the area is giving you the distance also. So all three things you can obtain with the help of speed time graph. So it's very important, because distance time graph was only capable of telling you about the distance and the value of velocity or speed, but this is capable of giving you speed, acceleration and distance, all three at one go. But you should know that gradient is giving us the acceleration and area is giving us the distance. So I think now you are well versed with the concepts, and we can talk about drawing different possibilities of graph one by one. I give you 1 minute, you write it down, and then we move on to the next section. All right. So next we wish to talk about the speed time graphs. Next we want to talk about the speed time graphs for various possibilities that we can have. Say for example, we are drawing the speed versus time graph for constant speed. So take your time, think carefully. We are talking about constant speed. Okay, constant speed. Speed is not changing. We are talking about uniform motion. Should it be a straight line, a straight horizontal line? Should it be a straight horizontal line? Why? Because the speed is not changing at all. So it is a constant graph, it is a constant speed. Okay, then we have speed time graph for uniform acceleration. So you all would know that uniform acceleration means that speed is increasing at a uniform rate. So it has to be a straight line. That means a uniform gradient, So gradient is same, the slope is same, and that is why it is the case of uniform acceleration. Third case, in fact, we are talking about increasing acceleration. So the gradient, are you understanding? Acceleration is increasing, speed is increasing, but acceleration is also increasing. So every time the rate at which the speed is increasing itself is also increasing. So let's say the acceleration for the first second is 5. So your speed will increase by 5. The next second acceleration becomes 7. So your speed will increase by 7. So the gradient is not going to be uniform now. It is an increasing gradient. So what should the graph look like now? If it has to increase the gradient. So less gradient, then more gradient, then more gradient. So acceleration is increasing. Speed is definitely increasing. Speed is increasing here also. But here the acceleration is also increasing. That is why the graph is having an increasing gradient. Okay, think about it. It is just the beginning of it. Then we talk about decreasing acceleration. So again, reminding you, speed is going to increase, but the rate at which the speed is going to increase is going to decrease. So it's the vice versa case. Maybe you had an acceleration of 7 meters per second square for the first second. The next second it became 5. So the rate at which your speed was increasing is in fact decreasing. But again reminding, the speed is still increasing. So I will draw the graph first and then you think about it. The gradient here is more. So the graph is more steep initially, then it becomes less steep. So it is indicating that the gradient is decreasing. On the contrary, here the gradient was increasing. Okay, Okay, think about it. Again reminding, constant speed, no change in speed. Uniform acceleration, speed increasing at a uniform rate. Increasing acceleration, graph becoming more steep. Decreasing acceleration, graph becoming less steep. Okay, finally we have uniform deceleration. What do we have? Uniform deceleration. So you are going on a trend where the speed is decreasing. So it is the case of negative acceleration. It is the case of negative acceleration. So what does that mean? The speed is decreasing. But for now we have taken the case only of uniform deceleration. So it is a straight line. So you look at all these 5 graphs at one go and you will understand the difference, how they are different from each other and how to extract information from it. Again, constant speed, uniform acceleration, increasing acceleration, decreasing acceleration and uniform deceleration. Draw them one by one in your notebook. I will wait, or you can pause the video and then we move on to the next slide. All right, so now let's take an example to understand this even better. Okay, so what is this example? Graph shows the speed versus time graph for a moving car. So now we have a speed versus time graph. Y-axis we have the speed, unit is meter per second, and x-axis we have time, the unit is second. First and foremost, what are they asking? Name the sections that represents, first part is steady speed. First part is steady speed. Okay, so let's call this O, let's call this A, let's call this B, let's call this C, D and E. Okay, so we have to name the section where it is traveling with a steady speed. Think about what we have just discussed. Steady speed, that means speed is not changing. So the answer for this part, the A part, that is steady speed, is going to be from A to B. Steady speed is going to be from A to B. Next part, it is speeding up. It is speeding up. So next we have to talk about in which part the car is speeding up. So what do you think? O to A, the speed is increasing very clearly, and it is also increasing from D to E. So O to A and D to E. Okay, then they are asking, it is being stationary. It is being stationary. So stationary, that is, it is not moving. Not moving will mean speed 0. So which part the graph speed is 0? From C to D. From C to D, the speed is 0, as you can see. And last part, it is slowing down. It is slowing down. So which part of the graph is it slowing down? So from B to C, you can clearly see the speed is reducing, or you can have a case of deceleration or negative gradient or negative acceleration. So the answer for this would be B to C. Okay, so this is the first part. I think everyone would be easily able to do this. Next is find the corresponding acceleration and deceleration. So now they are also wanting us to calculate the value of acceleration and deceleration. So what are the parts of acceleration first? So let's do that. Second part of the problem. Acceleration is happening from O to A. Again, reminding you, it is the gradient of the graph. So O to A, we are calculating the gradient, which is the acceleration. Acceleration. Let's write it A. Okay, what is it? So gradient, that is rise over run. So rise is going to be 20 minus 0 and the run is going to be 20 minus 0 as well. So the answer is going to be 1 meter per second. The answer is going to be 1 meter per second square. Don't forget, the unit of acceleration is not meter per second, it is meter per second square. Okay, next they are wanting us to find the corresponding acceleration. So now we will do it in one more part, that is from D to E, because it is also acceleration. Okay, so A is going to be rise over run, that is V2 minus V1 divided by T2 minus T1. So what is the value? So we can clearly see the value is going to be 30 here, and what is this value? 70 and 80. Okay, so what is V2? 30. What is V1? That is the velocity at D. It is 0. What is T2? It is 80. What is T1? It is 70. So this becomes 30 over 10, that is 3 meter per second square. So these are the two parts where the car is accelerating, O to A and then D to E. Next, we talk about the region B to C. This is where the car is decelerating. Okay, so A is again V2 minus V1 divided by T2 minus T1. Okay, so what is V2 now? Now V2, that is the final value of velocity, that is 0. Initial value of velocity is 20. Final time is 60 divided by initial time, that is 50. So this is going to be minus 20 over 10, that is minus 2 meter per second square. Minus 2 meter per second square. So the acceleration is negative. But if you have to answer what is the deceleration, so you can write it as positive 2. So you can write it as positive 2. So acceleration is negative, that is the case of deceleration. So you will state that deceleration is happening at the rate of 2 meter per second square. So the first part should be clear to all of you. Steady speed, speeding up, stationary and slowing down. What all sections are representing, that should be very clear to you. Second part, they also wanted us to give the values of acceleration and deceleration, which I think is very easy because we do remember that speed versus time, the gradient is going to give us the acceleration. Last part is the total distance. So you can pause the video, you can copy this down first, then I will clean it and we'll move on to the third part. All right, so now let's discuss the third part of the problem. The third part of the problem is saying total distance traveled by the car. So now they are wanting us to give the total distance traveled by the car. So now do you remember that speed versus time graph is not only capable of giving you the speed on the graph, it can also give you the acceleration because the gradient is going to give you that, but it is also capable of giving you the distance. How? By the area under the graph. By the area under the graph. So now what are we going to talk about? We are going to talk about area under the graph. So what is area under the graph? Are they asking the total distance? So that means we have to give the area under the graph right from 0 seconds to 80 seconds. That is going to give us the total area. And this total area is going to be divided in two parts clearly. The first part is the trapezium here. Okay. And the second part is this triangle. Okay. So what are we going to do to calculate the area? We will calculate it in two parts. That is area 1, A1 plus A2. That is going to give us the total distance. So what is A1 now? A1 is the area of the trapezium, that is half times the sum of parallel sides. So this side is 20 to 50, that is 30, and this is 0 to 60, that is 60. So the parallel sides are 30 and 60. Okay, so the sum of parallel sides is going to be 30 plus 60 times height or the distance between the parallel sides, which is clearly 20. So what is the value of A1? So the A1 value is going to be 900 and the unit of it is going to be meter. Why? Because it is meter per second multiplied by second. So what is meter per second multiplied by second? So it is going to be meters. Okay, what about area 2 now? So area 2 is going to be the area of the triangle, that is half times the base, that is 10, times the height, which is 30. So this is going to be 150 meters. So we have calculated both the areas. We don't worry about this part. Why? Because this part clearly means the car was stationary during this time. So it's not covering any distance. So what is A1? A1 is 900. And what is A2? That is 150. So the total distance traveled by the car is going to be 1050 meter or 1050 meter. So this class, this video was very important. We had discussed the basics of graph. What does distance time graph tell you? What does speed time graph tell you? I hope you were able to understand and also interpret the graph. So you should be able to draw the graph also, and you should be able to interpret the graph also. Next, we will talk about distance versus time graph in the next class, because it is going to be a very detailed analysis. Because distance versus time graph, you would say we have just done this in today's class, but then it was only for the case of constant velocity. So in the next class, we are going to talk about the various possibilities of distance versus time graph, that is including the component of acceleration also. It's going to be a very interesting class. Do see that class whenever you have time, but before that you do revise this particular thing that we've done in this class. Only then you would be able to correlate with the next class. Also, we are going to do some previous year questions in that particular class. But that's all for this class. See you next time. Thank you. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.